So this is now the final section of the course where we'll look at a couple of methods for calculating the area between two curves. Now the first thing we're going to have to do is decide what that means. And in particular, we'll give meaning to the phrase region bounded between two curves. Right? That's what we're actually going to give meaning to. And once we have done that, the second thing we'll do is decide on a strategy to calculate the area of such a region. Right? So that's what this section is going to be about. So let's start with this picture, which kind of comes with a question. So if I look at the graph here, and actually I'm missing a label on the x-axis, so I want to be consistent, so I'll just add that in now. So we've got the x-axis, y-axis as usual, but there's actually the graph of two different functions. There's a curve here that's concave up. That looks like it's the graph of some function g. You can see it's written y equals g of x is the label for this concave up function. And now there's also a concave down function. Right, and that one has a label here, y equals f of x. So this is the graph of some function f, this concave down graph. So there's a graph of two functions on the same graph, f and g. And what else do you notice? You notice they intersect at 2 points. Right, the two graphs intersect at this point here, which is an x-coordinate of a, and they also intersect at this point here, which has an x-coordinate, which is labeled as b. So that's what the picture is giving us. And it comes with a question. What is the area bounded between, well, there's two equations here, bounded between y equals f of x and y equals g of x. In other words, bounded between the graphs of those two equations. So first of all, what we're talking about, what we're actually talking about when we ask this question, the area bounded between y equals f of x and y equals g of x, is we're speaking about this area here, which I'm just going to gently shade in. I don't want to do too much because I'm going to add more to this picture. So this is actually the area that we're looking for. Okay, and well, in order to answer that question, let's take a look at what we can observe here. What if I made the question a little bit simpler? Forget about one of the curves, and what if I just talk about this area here, or the area of this region? So the one that goes all the way down to the x-axis has a line x equals a. This is the vertical line x equals a, and this is the vertical line x equals b. And so we're looking at the region that lies between the two vertical lines x equals a and x equals b, lies above the x-axis, but below the graph of the function f. Well, that's a little bit easier to answer. Right? That we actually already have the tools to identify that area. So and I'll do it in blue here. This is really just the definite integral from a to b of f of x with respect to x. Right, this notation is exactly the notation that describes the area under the graph of f between x equals a and x equals b. Right, so that is what we would get if we evaluated this definite integral. So is that going to answer the question? No, it won't, right? Because that's not what we asked. That's not what was asked for. What was asked for is this area in between these two curves. So we just want this well, kind of like a fish shaped up here, right? Or a really narrow, stretched out football. That's really what this area is here. But if we did this calculation, we're getting way too much area because we're getting all of this area down here that we didn't actually ask for. But there's a fix for that, because we can actually, this extra area that we've included in this calculation, we can look at that on its own as well. So if I did that, I would look at this shape here. If I trace under the graph of g in green, and then I draw down along the lines x equals a and x equals b as well, and then again use the x-axis as my bottom boundary. Well, now this area that's been outlined in green, this area in here, well, that's exactly the area that lies below the graph of the function g and between the vertical lines x equals a and x equals b. So that area we can actually calculate it directly. It's the definite integral from a to b of the function g of x with respect to x. So actually, that's going to give us enough to answer the question, because this area in here is going to be the difference of the whole area in blue, which can be calculated using this definite integral, and this smaller area, which was outlined in green, which can be calculated with this definite integral here. So that's the idea. Okay, so let's make one more note and then we'll answer the question. So one more note up here. You can use properties of definite integrals to make the following observation. If I subtracted those definite integrals, I don't actually have to compute two separate definite integrals. I can compute one. Because if I take the definite integral from a to b of f of x with respect to x minus the definite integral from a to b of g of x with respect to x, one of the properties says that I can actually combine that into a single definite integral. So that goes from a to b, and the integrand, the function inside, is f of x minus g of x. Okay, so that with this note and the observations we made over in this diagram, we can actually answer the question. So what is the area bounded between y equals f of x and y equals g of x? So what is this area here? Well, we could just write it down as follows. So the area is just given by the definite integral from a to b of f of x minus g of x. So in general, the f of x is your top function, and g of x is your bottom function, right? The function that is as the bottom boundary of that shape. So f is the upper boundary, and g is the lower boundary of that shape that you're trying to find the area of. And this will give you that area. So let's look at an example. Okay, so we're asked, what is the area bounded between the curves? And here are the curves. So, and if again, you want to relax your understanding of curve to include possibly straight lines, right? So we're just talking about graphs, really. So y equals e to the x, that's one of the curves. We've got y equals x, that's the identity line. X equals 0, that's the y-axis, right? That's the vertical line right along the y-axis, and then x equals 1, that's a vertical line right above, well, wherever I draw 1 along the x-axis. So if I just add a couple labels in here, we got x and y. Let's start with the exponential function. Remember the natural exponential function, it goes through the y-axis at the point 1 and goes upward like that. Okay, so that's what the exponential function looks like. The identity line y equals x, it's going to look something like that. Right, and then what else do we have? We have x equals 0, so the y-axis. I'll just trace this part about it over here to make it clear that that's actually a boundary for a region, and then the line x equals 1. So how about I put I'll put 1 over here, just because I drew that quite steep, so I don't want to go too far over. It'll be hard to draw. So this is going to go cause a boundary up here. And then now, usually when you draw a picture, like if I didn't have that picture and I just looked at these four equations, I don't have a very good picture in my mind of what region I'm actually, or what the region for whose area I'm actually trying to calculate. But now when you draw the picture, it's a bit more clear, right? There's one region here which is completely bounded. This one in here. We've got an upper function, the exponential function. You've got a lower function, the identity line, y equals x. Your left bound is x equals 0, and the right bound is x equals 1. So you have a well-defined shape here, which I can even just shade in for emphasis. How do I know we're talking about this region and not this region over here? Well, if it was this region over here, where's the other bound, right? There's no bound. If this line just keeps going down, and this curve just keeps going along closer and closer to the x-axis. So this, if you looked at this region over here, it's infinite. It's not a well-defined finite region, right? So, and same with over here. It's not this region because this line just keeps going, and this curve would just keep going up. So it would be an infinite region over here as well. This is the only sensible region that we could be talking about when we say the area bounded between the curves given here, these four equations. So how do you calculate the area? We'll just use the same strategy above. And one comment I'll make is that this picture that we started with, the left and right endpoints, which were given by a and b, those are the left and right endpoints of this definite integral. Those happened to be precisely where the graphs of those two functions intersected. But that doesn't always need to be the case, right? Just like this example illustrates that. If there's no intersection point at x equals 0, and there's no intersection point at x equals 1, so we're just going to use those vertical lines to actually bound the area. But that didn't actually happen in this picture. So I just wanted to draw your attention to that, but it's not important. It doesn't have to be the case every time you calculate the area between two curves that the curves are going to intersect at the endpoints, or even at all. Sometimes they don't intersect at all, like this example. Okay, so enough of that. Let's actually calculate the area now. So the area, I'll just write A for area. The area is going to be given by, well, the definite integral, and our left and right endpoints. So we got x equals 0 and x equals 1 here. Right, so that's going to be the definite integral from 0 to 1. Your upper function is the natural exponential function, y equals e to the x. So that's going to be the top function. That's like your f of x in the formula above, right? Our f of x is the top function, just like it was in this picture, right? Y equals f of x, that was the function whose graph was the upper boundary of the region. So that's why we're starting with the function e to the x, because that's the upper boundary. And then we're going to subtract, using this formula, we're going to subtract the function who forms the lower boundary, which is this identity line, y equals x. So we're going to subtract x. And then, of course, that is going to be calculated with respect to x. Now, this is really often, this is the trickiest part of these problems, is setting up the actual definite integral that you need to calculate. And once you've set it up, well, the rest is step by step and systematic. And as long as you follow the rules and take your time and go carefully and watch out for math errors, which are easy to make, but you'll get the right area. Most of the hard work is done here. Now it's just a matter of evaluating it. Remember how we evaluate these? We need to find an antiderivative of e to the x minus x, and then we'll just plug in the endpoints 0 and 1, and then subtract accordingly. That's using the fundamental theorem of calculus, part 2. So our antiderivative, well, we can do it term by term because they're subtracted. So an antiderivative for e to the x, well, it will just be e to the x, since e to the x is its own derivative. And then for x, well, we can use the power rule, the antiderivative power rule for x to the 1. So we're going to end up getting x to the power of 2 divided by 2. So that's the antiderivative, and then we're going to plug in the endpoints 1 and 0, and then subtract. So let's go ahead and do that. So we'll plug 1 into all of this, so we're going to have e to the power of 1 minus 1 squared over 2, and then take everything and plug in 0. So we'll have minus e to the 0 minus 0 squared over 2. So actually, once you clean this up, this is really just e minus 1/2. Right, 1 squared is 1, so this is just 1/2 minus, this will just be 1, because e to the 0 is 1, and then 0 squared over 2, this is just 0. So you've got e minus 1/2 minus 1. So that's just going to actually work out to be e minus 3/2, and that's your area. That's the area that is bounded between the graphs of these 4 equations that we've highlighted in green.